researching into the wind. So I'll let him do the rest. Thank you.
Tēnā koutou, tēnā koutou, tēnā koutou, katoa. Well, translating that, greetings, greetings, greetings to you all. If you don't recognise the language, that's Maori, the language of the indigenous people of New Zealand. I know full well this will not be the only Maori that's spoken in Edinburgh over the next few weeks, because the All Blacks are coming this way, and they always start their matches with the haka, which is also, of course, in Maori. That's the limit of my Maori. I sort of end about there. A couple of weeks ago I gave a similar presentation in France, and I did translate it into French first, but my French is not much better than my Maori, but I survived over there for a month. What I want to talk to you about today is nothing terribly sophisticated, but is some general observations and some thoughts about mainly experimental but numerical techniques for trying to understand not so much the wind itself, but the effect that the wind has on various things. And I'm going to do that by looking a bit at sort of the wind friend and foe. And I picked a couple of pictures here to start with. On the left, we have a couple of yachts sailing in the Louis Vuitton Pacific series a few years ago out on the harbour just outside of Auckland. Nice place to go sailing. If you're not too sure where Auckland is, it's towards the northern end of New Zealand, up here. Sometimes known as the City of Sails. It's been said, but I don't know whether it's totally true, that Auckland has more yachts per head of population than any other city in the world. There are certainly a lot of them, and on things like Auckland Anniversary weekend, you can have 1,000 yachts and dinghies out there on the harbour sailing in a variety of races. I'm not a great sailor. I've spent several years teaching kids the basics of sailing on the harbour here. And I enjoy going out with our yacht research unit and doing full-scale testing of yachts. We do a lot of wind tunnel testing, and that will come through this talk. But it's quite fun sometimes to get out there on the harbour. I was just saying before that Auckland's not a particularly windy place, but it's sort of moderately windy, except of course when all your instrumentation is working and you're ready to do a full-scale test, and that's the time that the wind dies. Either that or it increases fivefold and you're out there in a gale. A couple of years ago we had just bought a brand new Spinnaker to do some testing. We went out on the harbour, put the Spinnaker up and immediately ripped it in two. A very expensive start to an experimental program. But I'll come back to that. The wind, though, can be damaging, and I'm going to try and balance that up. Certainly at one side of my research is wind loads on buildings and structures and the damage that can do. And I picked a photo here of a building with the roof ripped off it. It's part of my own sort of personal collection because I've actually slept in that building. It's on the east coast of Nicaragua in Central America. Admittedly, it wasn't quite as well ventilated while I was sleeping inside there. Wasn't the most comfortable experiences. I basically had a foam mattress on a wooden floor and a mosquito net sort of over the top of me. But it's better than some places in some ways. But that building was built as a storm shelter. Probably wasn't built strong enough. Now I first went to the place where it is, which is a village called the Barra, out there on the east coast of Nicaragua. The Barra's sort of not the easiest of places to get to. You first of all got to get to blue fields down here on the coast. The roads that go from places like Managua, the capital, stop at this point. Generally I've flown into Bluefields. This year I was there in late January, and for the first time I actually went overland, which does mean going by road down to Rama, and then you take a boat down the river to get there. When you get there, there's roads and there's vehicles, but there isn't actually a good road between the two. There is a rough track that a four-wheel drive in the dry season might get through, but you're isolated even there to a certain extent. And then if you want to get to La Barra, you then get in a hangar, something like that, and go for about 4 hours by boat up the coast through the inland waterways. Can be a bit rough at times. And why on earth would you want to do that? Well, I've been there with a charity, originally in 2005, trying to install a mixed solar and wind power system simply to charge batteries. At the time there was no mains electricity in the village. Typical homes look something like this, and just providing simple 12-volt lighting can make a lot of difference to communities like this. But you are struggling in many ways. We installed a couple of small wind turbines, 1 kilowatt sort of size. And I just stuck this photo in because, again, coming back to the sort of damaging winds, this is actually the school in the village there. Now, this is early 2005, and they were getting ready to put the roof on. Somewhere during that year, they did manage to get the roof on the school. Unfortunately, in October of that year, a hurricane came ashore, and the centre of it came right over the village. Had a number of damaging effects. For a start, it ripped the roof off the school. And this is some 15 months later. You can see not only has the roof come off, but also the top of the wall is now disappeared. Government agencies out there don't work terribly quickly. So 15 months later, the school still didn't have a roof. The kids were being taught actually underneath that storm shelter that had its roof torn off, not in that particular storm, but later. And the small wind turbines that we'd installed, well, one of them fried itself, and apparently there was sparks flying out of it during the hurricane. The other one had bashed its blade tips against its support structure and had certainly suffered some damage. The brown one there that just coming into the picture is the new one that we were installing at that time a couple of years later. But after a couple of weeks work, then we had a couple of new wind turbines up, or repaired a new wind turbine to go alongside the solar. These days they actually have got some mains electricity in the area. One of the problems we had actually in doing this repair work was the fact that somebody else had built this storm shelter right in the path of where the mast for the one on the left hand side was actually meant to fold down. So we actually had to try and get the mast down without using its normal hinge, which meant we actually broke it in two, which is another story. But we did get them back up and get them running again, at least for a time being. But what with hurricanes? The turbine on the left actually suffered from corrosion and had to be taken out. The one on the right suffered from a bird strike from a small vulture that flew through it at some stage. In the end, the charity I was working with has actually given up on the wind turbines. They're sticking with the solar. The reliability just wasn't there, and certainly extreme weather can be part of that in an area where you're battling. The building originally looked like that. A later hurricane came through and ripped a section of the roof off. And I guess what I'm saying there is that certainly, the wind can provide green energy, but you do have to design whatever it is to withstand the extremes. Now, knowing what your extremes are going to be is an important part. What are your loads? How can you mitigate for those circumstances? I mean, even these small wind turbines were supposed to have furling mechanisms such that they turned out of the wind, but it still didn't save them. What I want to look at really in the talk, though, is different approaches to trying to understand the effects of the wind, whether from a damaging point of view or a useful point of view. And from that end, I'm going to look at full-scale testing, wind tunnel testing, and computational modelling. I'll start by looking at a diffuser augmented wind turbine. Now, this is the Vortec 7 DAWT, diffuser augmented wind turbine. Just over 7 metres in diameter, the rotor there. It was based upon a design that came out of Grumman Aerospace in the US. And there were a company, Vortec, were a venture capital company that bought the rights to this design. Now, the trouble was that they bought the rights and they told their investors that according to the experiments that had been done, this turbine could, well, the data varied, but the data suggested anything like 4 to 8 times the amount of energy you'd expect out of a standard horizontal axis wind turbine of the same diameter. And of course, if the data said 4 to 8, the people who were trying to sell the ideas, of course, told their investors that it would produce 8 times the energy of a bare wind turbine, that the diffuser would hugely increase the energy output. Unfortunately, the reality was nothing like that good, which is partly why they then came to the university and said, well, it's not working as well as it should. What can we do about it? And we got involved in a number of ways, along with others, at looking at what was happening to the flow. On the left, you've got some streamers just showing that through the diffuser, the flow was doing what our computational model said, which was it was sticking to the diffuser. It wasn't actually slowing up as it should do. It was just ripping through there. It wasn't creating the conditions that one wanted. We looked then at, well, what could you do with the design? It was quite crude, so we came up with some suggestions, various sort of fairings, trying to improve the aerodynamics. Our modelling said that should improve its performance, and so we're using computational modelling, and we were predicting that with the various modifications we could go up. And of course, with something like that size turbine, making the modifications isn't cheap, and so if you can at least eliminate some of the ideas that perhaps aren't going to be as good in the first place, then it's a lot easier to then sort of say, well, these things are the ones that are probably worth trying to do. And a number of those were put into place, certainly the nose cone, streamlining the nacelle and those sort of things. And just in this clip of video, one can see that at this stage it's got a nose cone on it, man walking past the front there to give you some idea of the sort of scale. Trouble with this huge great diffuser though is you've got to actually turn the whole thing to face the wind, and that has implications. You can see it rotating around there. The improvements did put up the power output, but not astronomically. And so, you know, you then go back and sort of say, well, actually, the aerodynamics are quite crude. We think we could do better, and we came up with some ideas, including this rather more streamlined nacelle, diffuser, and predicted what performance we thought that should give us. Do note this is the basically the augmentation on the left-hand side there. So we're saying we think with these improvements we might get double the power output from a bare turbine. Not 8 times, just double. Even with some of these. Built a wind tunnel model. Just at the time that the model had been completed, our own wind tunnel decided that it didn't like holding on to the tips of its blades when running at full speed, and these are 3 metre diameter blades, and about the 8.5 metre section of one of the blades came off. It then ripped the tips off the next 2 and banged holes in the framework and such like. And so we were left with 6 months of repair, it turned out in the end. And so this model went off to Melbourne and was tested in a wind tunnel over there, which was possibly slightly too small. When the experimental results came back, the wind tunnel results up here, this is the power against disk loading from the testing, and the maximum sort of upper end what we were predicting from the CFD. The only trouble was that when you actually looked a bit further, you found that the base pressure down here was in the wind tunnel, it was a lot lower than we were expecting it to be. And one sort of says, well, why is that? Part of the answer was that the wind tunnel really was too small. It was a lot smaller, something like half the cross-sectional area of our own tunnel. So it was having an effect. So we went back to the CFD and sort of said, well, what if we put boundaries in at the same sort of size, effectively, as the wind tunnel? And then we got much better alignments with the extra effects of blockage. CFD versus wind tunnel, but now the wind tunnel sort of, or the CFD prediction is saying, well, it should be up here. We're not. Why? Well, the wind tunnel actually then provided the answers. I can remember climbing into the wind tunnel with a long stick with just a cotton tuft on the end and poking around, and you could see that the flow wasn't as nice as our CFD model said. It was separating somewhere over here, and therefore the flow through the slot here was nothing like as strong as we'd hoped. So you go back to the CFD, reanalyse how you're treating the boundary layers, find that with a bit of improvement on that you then get this separated flow, which then sort of says, okay, go back, think again. And we did go back and think again, and we came up with another idea where now the flow into the slots came in through the nose. This is a bit dark, I'm sorry. This is our multi-slotted version, and that then was wind tunnel tested in various ways. Wind tunnel tested, but also some small prototypes, nothing like as big as the Vortec 7, but a couple of metre diameter sort of ones. One that I never actually saw happen, but I was away at the time. They actually did some testing, mounting one of these diffuser augmented wind turbines on a trailer and towing it up and down a runway. It's one way to create a known wind speed and a variable wind speed. I'm not too sure exactly what the logic behind that was, but I always found that a sort of interesting little bit of experimenting. Now, at the end of the day, though, this showed some promise. Not as good as the original predictions, but you then sort of say, well, okay, but we're going to have to design a diffuser that's going to have to withstand the strongest winds that it encounters in 50 years or 30 years or whatever period you expect it to last. And it was that that actually killed the whole project. The company, Vortec, folded up. The shareholders lost all their money that they'd put into it. And it really came down to, okay, maybe if it could have done the 8 times bare turbine energy, it may have been worth it, but I'm still not too sure. But certainly the structure that was needed for that diffuser to survive the worst storm it's likely to in 50 years or something, just made it too expensive. You can turn the diffuser to sort of minimise its resistance to the flow, but you can't completely sort of take it away. You can't do what you can do with more conventional wind turbines and sort of reduce the wind loading under those extreme storm conditions. And so certainly in that case, it was the extreme loading that killed the whole project rather than the aerodynamics, although that was difficult. Now I picked on that one because I think it illustrates that in some ways the sort of combination of full-scale testing, wind tunnel testing, computational modelling, sometimes one would show you where the deficiencies are in the other. If you focus on one approach and one approach only, you can make some sort of significant errors, I think. You can miss things. And so certainly I think the combination of these different approaches to trying to understand the wind and its effect, it is quite powerful. Now, certainly over the years I've met a number of people who've sort of specialised, and perhaps I haven't sufficiently in terms of, I'm probably a bit of a generalist in that for something like 30 odd years I've had a foot in each of these camps, in full-scale testing, wind tunnel testing and computational model. I wouldn't say I'm an expert if anything, probably the top one is the one that I probably am better known for the sort of being involved in, particularly with buildings, but with other things as well. And so I want to just sort of look at each of those and look at some of the strengths and weaknesses of each approach to testing. Strengths and weaknesses of full-scale testing. Well, one of its greatest strengths is it's the real thing, or at least nearly. I hope you don't get seasick watching this bit of video. This is actually one of the most difficult pieces of full-scale testing I know. It's quite pleasant, but it is difficult. Because if you're trying to measure the forces on the sail, or the pressures, which we also try to do, you're dealing with something that, A, is a moving object. Its geometry is not absolutely fixed, so you don't know what shape it's going to be. Your sails themselves you trim them, you adjust them, depending on what direction you're sailing in. So if you're going to be measuring pressures, you've actually got to also capture what the shape was at the time. And that's why they've got orange stripes on them. We use a camera system for capturing the shape. Often in other experiments you stick up an anemometer and you measure the wind as it approaches your building, your structure, whatever it is, your wind turbine. Difficult to do with a yacht that's sailing around. I'll talk more about that one. The boat itself changes its attitude depending on how highly loaded it is. It tips over. It also reacts to waves and such like. So full-scale testing, I think, on the yachts, which we are trying to do and trying to do more of at Auckland University, is probably one of the hardest bits of full-scale testing I've come across. And we struggle with trying to get all the instrumentation working simultaneously. It's not necessarily a kind environment as well, and on occasions you're in danger of sort of dropping things in the ocean, which doesn't help. So, I say it's the real thing, or nearly. Yeah, there are times when it's slightly artificial, but it's nearly. But certainly nature is your enemy, or at least usually. Occasionally, very occasionally, nature may actually give you something nice. I quite like these photographs of the snow around one of the buildings I've worked on. This is a also structures building down near Bedford. The snow there gives you a very nice idea of what the flow is done. It's coming impinged on building, coming back round. There's a ground separation line down there. Up on the roof, you can also see that one's got a flow separation and then there's a recirculating flow onto the roof. So very occasionally, nature can help you, but most of the time it's a problem. These static pressure probes that are poking up through the roof here are there partially to stop rain getting into the instrumentation. There's various ways of solving that, but rain is always a problem. You're dealing with a real environment. Certainly, this is actually a shot from a test building in the United States. I visited, I haven't worked on it, or at least not in the full scale. I've worked on wind tunnel models of it. But they have a system where they're simple tap, but then they actually have to have a drain to catch any rain and then drain it away. And there are a number of other things in nature that tend to work against you. On many of these buildings, we tend to use pressure taps, something like 7mm in diameter, and then tubing from there. 7mm in diameter, certain types of wasp think are ideal nesting spots. I have spent a not terribly pleasant day cleaning the tubes out from one of the buildings I've worked on, just cleaning out the wasp larvae and such like from inside. Rats like to chew cables if you're working outside, so one's always got to sort of be aware of those, and there are a variety of other things that can work against you. If you're doing full-scale testing, then often just checking that everything is calibrated and working okay. If you're measuring pressures, you nearly always want to sort of zero your instrumentation. Calibration very often is more reliable with pressure transducers, but zero levels do drift around, and so one often needs some sort of mechanism for applying same pressure across a differential pressure transducer. If you're out in the natural wind, you simply can't switch the wind off. It's a nice thing about wind tunnels. You can hit the stop button, zero everything, take a new reference level, carry on with your testing. Difficult to do in full scale. One's often trying to get a reference dynamic pressure and a static pressure. That particular setup there, along with a sonic anemometer for measuring the wind, is in front of a 2-metre high wall that was used for sort of design load calculations for brick walls around England as much as anything. But one's trying to get those things and then feed them in. If you're dealing with the wind, then static pressure is not static though. It is a fully turbulent flow. There are vortex cores, and even if you do measure the static pressure, it actually comes through as quite a fluctuating pressure signal. Certainly in one set of testing we did on one building, you could see that at one stage there was a very high positive pressure came through on all the different locations simultaneously. Nothing to do with a large sudden dumping of wind or something. It was actually coming from the suction side on the reference pressure, and we weren't filtering that out enough. We weren't damping down the static pressure being put onto the backing side of the transducers, and so they all saw this fairly significant suction pressure transmitted through. So if you're not careful, you can end up with erroneous answers simply because of nature working with you. And some of those static pressure variations can be quite significant. Coming back to this picture from inside the Texas Tech building in Lubbock, Texas, a lot of these solenoids and such like around the place are simply so that every now and again you can apply the same pressure across your transducers and then apply a known pressure to check its calibration and such like. Possible with those things, but if you're working on sails, and here we've got differential pressure transducers on the sails themselves. Difficult to put solenoids to switch connections and such like onto the sail itself without causing all sorts of interference. The only way that we have of getting zeros is to take the sails down completely, stick them into their bag, take a set of zeros and then put them all back up again. So it's a half-hour job just to get a set of zeros, but it does need to be done periodically. With full-scale testing, there's often a problem with actually knowing what the wind is doing. You can only actually measure it remotely, so you can get certain statistical things, but you don't actually know exactly what the wind is doing at the structure you're looking at. And that does get worse with this yacht testing. We can do things like stick a 3-component sonic anemometer up on top of the mast, but the top of the mast doesn't stay stationary. So if you measure up there, then you measure a mixture of what the wind's doing plus what the top of the mast is doing. Often we'll put an inertial measurement unit up there as well to try and actually find out what motion we've got. We've tried subtracting one from the other, not with complete success. One can see the relationship between the movements and what the sonic's measuring, but trying to actually get back to what the wind was doing is difficult. On some of the testing, we stick another one off the stern, but certainly if we've got a sonic anemometer down here, it's affected by the flow coming off the sails, and so you measure a modified wind field. Even at the top of the mast, you're often measuring a modified wind field, and you've got to try and compensate for that. From the masthead one, I just put this up. This is the 3 components of velocity measured on a masthead. And along here, this appears that we have this nice sort of sinusoidal set of wind fluctuations that occur. Anybody like to suggest what that actually is? No? Good try. Yeah. It's actually the wave pattern from probably one of the catamarans going out to Waiheke Island, one of the fast boats. So our yacht is obviously sailed through a set of waves, and so this has got nothing whatsoever to do with the wind. It's just one of those interferences, as I say, you can try to get rid of, but it makes life difficult. Also with full scale, pretty well no experiment can be exactly repeated. If you're testing in the wind tunnel, sometimes you can do multiple tests to look at things like extreme values, and you can do an extreme value analysis of your results. If you're doing full scale testing, you never exactly get the same conditions again. They might be similar, but they're never exactly it. And just trying to deal with the data is part of the problem. This is one experiment I was involved in a lot in 2000. The Silso cube, it's a 6-metre cube. We're measuring pressures at various points on the building, horizontal ring of taps and a vertical ring. And those pressures are highly fluctuating. We measured for multiple 12-minute periods over several years, in fact. But no single 12-minute period is exactly the same as the next one. If you look at some of the statistics, things like the ratio of the maximum dynamic pressure during the observation period to its mean value, there's a range of conditions that come through there, partly atmospheric stability related and such like. And you've got to try and deal with that. You can't reject everything. We generally fairly standard mean pressure coefficient. That one's dead simple. But then you sort of start to say, well, what do you do with the sort of fluctuating, the standard deviation of pressures? And we reckon that one of the best ideas, very often with this fully turbulent wind, is to ratio that to what the standard deviation in the wind was for the same period. And that then gives a reasonably sensible variation. This is for one of the taps. This is H1, one sort of near one of the vertical edges on the horizontal ring. The mean pressures come out in a reasonably tight pattern. Standard deviations in blue there, a slightly bigger spread. If you start to look at maximums and minimums, which are of interest to wind loading, what's the maximum suction I'm going to get that might rip something off my building? Then, again, we reckon that to ratio the maximum to the highest dynamic pressure and even the minimum to the highest dynamic pressure is the most sensible thing to do. And there you get a lot more scatter, much more difficult. You can't do this sort of extreme value analysis readily on this data because two runs aren't quite the same thing, and so one's often trying to understand these things against the odds almost. Full-scale testing can very often be expensive and take a long time. Very often, if you're looking at trying to measure things in the wind, you need at least a year's data, if not several years, to really make sense of things. If we switch then to wind tunnels, you know, one of the things that you have with a wind tunnel is you actually have control of the wind. I've already said you can switch it off when you want to. You can control its speed. These are the new intake fans on our Auckland wind tunnel. 2 3-metre diameter fans, each of them only make 45 kilowatts of motor power there, but that's enough from our point of view. Obviously these days variable frequency drives, so you can control the speed, and we control that for the testing. Most of what we do, not all, but a lot of what we do is for yachts and yacht testing, and we don't need particularly high wind speeds for that. In fact, our models are moderately fragile, and if we did crank the wind speed up too high, then we'd have broken models before you can look at you. I spent 5 months this year, though, working in this facility. This is the Wall of Wind at Florida International University. You can get an idea of the scale of this one by the man walking past. So it's 12 1.5 metre diameter fans. Each of those fans is not 45 kilowatts but 500 kilowatts, so it's a 6 megawatt facility. They can control the speed, but only in a fixed sense. They can't fluctuate the wind speed. Looking at it from the other side, then it comes through and there's some roughness elements to create a bit of turbulence on the floor and such like. 6 metres wide, 4.5 metres high, the working section there, and they can subject things that are getting near to real life. It's not a complete building, but it's reasonable size, and they can do a test where they take a section of a roof, and down here we've got the speed in miles per hour coming up as it's gradually cranking up there. You can see local deformation. I was quite disappointed actually in the 5 months I was there. I never actually saw anything completely rip apart and sort of fly out of the building. Did see 1 or 2 things getting damaged, but one can subject, we're getting up towards 140, nearly 100, we've stopped for some reason. Putting my hand there obviously, gone this way, we'll probably stop again just to be difficult. I wanted it does go up to 157 miles an hour at the top speed there, which is hurricane force 5. So one can take things up to sort of conditions where you can subject things like a rooftop solar panel or something like that to the same conditions, and various other sort of bits and pieces. Some of the other roofing materials that work. So
it's your hand operation that's doing the.
I didn't touch anything. So, yeah, but you could be right. Something. So you can, you know, in wind tunnels you can control the speed, you can do a variety of speeds, it's under your control. In the wind tunnel it doesn't usually rain. I say that, one of the things that's perhaps a little bit unusual about that wall of wind facility is that if it does rain they have to stop because they're actually drawing the air in from outside and blasting out the other side, and rain is bad news, so if it starts to rain the whole facility has to shut down. If they actually want to test, and with these roofing bits, they do want to also test with rain, so they can do rain wind simulation. Up here there are actually rain generators, so they can artificially create rain downstream of the fans and subject the building. After all the pressure measuring and displacement measuring electronics has been removed, then they can set it up with just rain capture systems to see whether it's leaching, having been subjected to hurricane force winds. Wind tunnels do have the advantage that the models are relatively cheap. I just pulled out some figures for Ericsson 4. Over here on the left we have our Ericsson Volvo 70 model, which I think costs about €2,000. I did this slide for when I was speaking in France, so it's in euros. Now, I did find that last year on sale, having just reduced the price by €250,000, it was down to a mere €650,000 to buy a real one. So if you're testing, and some of these syndicates will sometimes sort of do some of their development by having two multi-million pound yachts racing against each other. But you can only do a limited amount of that. For the cost of one of the sails for the full-size boat, you can probably make 20 sails to test in the wind tunnel. So if you're going through initial stages trying to figure out what combination of sails, it's a lot cheaper to do that in the wind tunnel. There are problems in the wind tunnel. Some of them you can overcome. Sticking with the yachts. Yachts move, wind tunnels models stay still. In reality, a yacht will be sailing at some sort of boat speed. It's then seeing the wind blowing over the sea, coming at it, and what it sees is an apparent wind, and that makes life a little bit difficult. In the wind tunnel, we basically model the apparent wind and the apparent wind angles rather than the true wind. But if you do the vector addition at different heights, then you find that at different heights the wind's actually coming from different directions. This was recognised back in the 1990s and was the reason why in the early 1990s Auckland built its first twisted flow wind tunnel. This is now version about 2.5 or something. It's now been moved again, but it's been rebuilt and reshaped a few times. And the thing is that particularly when you're sailing downwind, when you've got the spinnaker up and such like, the flow comes onto the boat from different directions, and so we're using this sort of vertical Venetian blind type system such that the flow down low is coming more onto the bow, and up high it's more coming across the boat. This creates a more realistic testing situation, which is significant enough for downwind sails. If you're sailing upwind, sailing into the wind, then it doesn't matter too much. A few degrees of twist is about all you get. But downwind, it is quite important. And certainly the testing that was done in the twisted flow wind tunnel in the early 1990s is attributed as being one of the factors that led to Team New Zealand winning the 1995 America's Cup. The second team to get the better of the Americans at that game. And that's still our sort of workhorse. There's also the fact, I mentioned it earlier, yachts sort of heel over if the moment increases, and to deal with that we have a thing called the Real-Time Velocity Prediction Program. A VPP predicts what the boat will do given a set of loads. Now what we do, often you just use analytic models in here, but what we do is to interface the wind tunnel. So we take the forces from the force balance, measurements of the wind pressure in the tunnel, measurements of what angle the boat is heeled to at the time, do some calculations, say, but actually with those loads, the boat would heel over to 20 degrees or whatever it is. And so we feed that back through a controller and adjust the heel angle. So here's a little video where at the moment the sails are depowered, they're not at full strength. and they're twisted so that they've got little power on them. Over on the left, we have indicators here, both graphical and digital, of the boat speed in knots and the heel angle, which currently says 9 degrees. Now, with our models, we also have remote winches. Somebody will stand on the side of the tunnel and make the trim adjustments the same that the real sailors would do in reality. So, is that going to work? Well, let's see if we can. It worked before. I checked this earlier. No? Sorry, you're going to have to take my word for it. As the loads come on, we actually then can control the heel angle and the boat will heel over. And also it means that you can trim to maximise the boat speed because it's telling you a whole variety of things, how the forces are interacting. Under the floor of the turntable there's a 6-component force balance telling you what all the moments and all the forces are, and so you can feed that into the program and sort of have it reasonably realistic. For some of the most sophisticated testing, then we're also, if we're testing for a racing syndicate, sometimes we'll bring their trimmers in off the boat and they'll actually do the sail trims because they know what the sails should look like, and so we use real trimmers rather than amateur academics. Certainly in wind tunnel modelling you can't always model the turbulence completely. This is a 1/40th scale model of the Sulso structures building, the Sulso cube. We can set up roughness, but almost inevitably in the wind tunnel you don't get the very low frequency stuff that you might have in full scale. In something like the wall of wind, here's a 1/5 scale model of the cube. You're even more restricted in terms of the low frequency content, and so one has to try and deal with those things. And certainly you can't always do everything that you should do. You very often have compromises. This is some testing we did last year, yes, where we're looking at interference between multiple yachts. To do this, we want to put a second model yacht upstream and then see what that's doing to the forces on the boat itself. We can look at reductions in drive force, but also on the side force, and try to understand how two boats are going to interfere with each other. We do the same with boats sailing downwind as well. Now, when we're saying downwind, we really should have twisted flow in there. But if you want to put the second model 8 metres upstream, then either it's going to be on the other side of the turning vanes, which is probably just going to mean that the results are rubbish, or you actually want to put that boat right where the turning vanes are. So it's not really feasible, so you do it without. But you are making a compromise. You hope that the results that you obtain there are still reasonably representative, but you can't always do everything that you want to. Touch on CFD a little bit. Advantage with CFD is that you only need a computer and the software. Now, sometimes that might be rather demanding in itself, but you don't need real physical facilities. One of the advantages is that you have information on the whole flow field. This is an example, downtown Auckland. This building here, 1 Queen Street, it's known to create very bad wind flow around the bottom. If you're in the wind tunnel, you can do a variety of things. This is using scouring techniques, but you can also put instrumentation in there, hot wire anemometers or cobra probes, and measure. But you're often restricted in terms of measuring at particular points. With the CFD, you pretty well have access to the complete flow field once you've got a reasonable model. And so you can look at that and sort of say, well, what is happening in this region? Why are we getting these very windy areas? Partially, it's the interaction between this building here, the ferry building, and number 1 Queen Street, which creates a high pressure. The orange bit there is pressure coefficient of 0.3, ISO surface, and it's showing how that sort of higher pressures on the upper part of the building are then deflecting the wind down, which then curls around the corners. Modelling flow separation is difficult. If you've got attached flows, CFD is very reliable. I think if you've got separating flows, it still is very difficult to get it right. This is fairly old. This was some flow around just simple models of Spinnaker. Here, using UV light and white tufts, one can see where the flow separation is. And our CFD modelling at the time gets that reasonably right, but it's one of those things where it tends to do worst under conditions that you perhaps are most interested in, somewhere around here, where the wind tunnel and the CFD models sort of have the maximum differences. Certainly, trying to get the flows to separate in the right place is still a very difficult thing. It's not always obvious how to model everything. One of the earliest cases I looked at with CFD modelling was trying to do windbreaks for protecting kiwifruit. And you know, even then there was a question of, well, how do you do that in your CFD? We went for sort of just using a resistance coefficient to characterise the flow through the windbreak, and it gave us reasonable results. These are quite old now. But there are a number of challenges over the year where similar questions, you know, got involved in modelling extrusion of metals. How do you model the viscosity of an extruding metal? And with aluminium, it was particularly interesting in terms of trying to deal with the fact it's strain hardening as well. Yep, okay. We did some work on sterilisation of canned foods. And here, I think the interesting thing is we're not only solving conservation equations for velocities and such like, but we're also actually solving conservation equations for the bacteria and then vitamins C, B1 and B2. We set up in the CFD code the actual conservation equations for destruction of bacteria and also simultaneous destruction of vitamins, and so one can try and optimise how to destroy the bacteria without killing the food, if you like. Turbulence is always hard to model. In the atmosphere there's lots of variety of length scales. CFD, that's hard as well as in the wind tunnel. Been quite pleased with some testing we've done recently on using large eddy simulation on the cube. We're interested, particularly in this region here, where the minimum pressures are more than one might anticipate from simple theory. And it comes back to some of these big pressure spikes that occur. And we've looked at that in terms of the full scale, conditionally sampling the answers, and one gets a characteristic pattern coming through, both on sidewalls and similarly on the roof. And that shows up also in velocity measurements. We then sort of done a bit of flow visualisation. Seems to be associated with vortices forming on the roof intermittently, some of them quite strong. And we get the same sort of thing in the wind tunnel. And then we've done large eddy simulation on the cube. Gives us reasonable pressure distributions, reasonable flow separation and reattachment, and we get the same sort of patterns coming through, and so we can then use that to understand what's happening and to try and sort of look in the CFD, again when we have access to the full flow field, and so we can see the formation of vortices that are associated with these high suction peaks. Last few comments that cross some of the boundaries between this modelling. One wants geometric scaling, but there are limits to what you can do with geometric scaling. With models, we can usually do it, but if you scale down from the full scale to the model, often your strength has dropped as well, which puts limitations on things. With windbreaks, we can't scale down either in the wind tunnel or in CFD. You know, the 2 or 3 millimetre diameter holes, so one has questions about how do you do that. The wind tunnel, we might actually just stick with the same size hole because it then gives the right sort of through flow. One should match Reynolds numbers, but often that is not reasonable. If we try to match the Reynolds number in going down about 10th scale here, if we put the speed up tenfold, the mast just wouldn't stand the loads, and so we have to work at a lower Reynolds number. And so one needs to recognise what effect that might have. The last one I want to touch on is, well, sometimes you want to match Froude numbers. Now, most people think about this in terms of sort of waves and wave propagation, those sort of things. But the example I want to take here is actually an unusual one, and that's roofing tiles coming off buildings during hurricanes. This is a picture from Hurricane Yasi, hit Cairns area a couple of years ago. roofing tiles ripped off the roof, and they fly through the air, they punch holes in roofs, they smash windows. And we've been looking at some of the flight of these, and there is a tile that's there at the moment, it's just coming across. This is a wind tunnel modelling. The nice thing here is that if we go down in scale, say to 1/10 scale, the wind speed comes down by √10, and so we can actually maintain our fruit number scaling, which gives us a model version of the flight of a roofing tile. For some of this, we can then track where that's gone. If we know the times of where it was, we can work out how its velocity was increasing. And we can combine that with things like CFD modelling to give us a flow field, and then a 6 degree of freedom trajectory model to say where the tile's going. Takes me back to my PhD work on low velocity ballistics. And we get reasonable correlation here. And you know, one of the things you're looking at here is, well, how quickly will a tile pick up the wind speed? Because you want to know how damaging is it going to do, or how much damage is it going to do when it hits something else. And in that case, we can actually do the fruit number scaling, but there are other times when you can't. So in conclusion, I suppose what I've just tried to say is, well, full-scale testing, wind tunnel and CFD modelling, they all help in our understanding. They all have their strengths and their weaknesses though, and one needs to recognise when you're pushing the boundaries and what your limitations might be. Certainly anything that's subject to the wind needs to be designed to withstand its extremes, not just its intended operating conditions. And I would certainly say that the wind can be both friend and foe. Thank you.
This production is brought to you by the University of Edinburgh.